What if I told you that the most powerful telescope ever built by human hands, a $10 billion machine floating silently at a point 1.5 million kilometers from Earth, was never supposed to look at the closest star to our Sun? What if I told you that when a group of scientists finally convinced NASA to turn that telescope toward our nearest stellar neighbor, what they found was so unexpected, so strange, so profoundly unsettling to everything we thought we understood about nearby planetary systems, that the entire astronomical community went into a frenzy? And what if I told you that after they found it, they looked again a few months later, and the thing they had discovered had simply vanished, as if it had never been there at all? This is not science fiction. This is not a movie trailer. This is real. This happened. And by the end of this video, you will understand every single detail of what was found, why it matters, why it disappeared, and why this single discovery might reshape the entire future of human civilization's relationship with the stars. But before we get into any of that, I need you to understand something fundamental. I need you to truly grasp, in your bones, not just in your mind, why the Alpha Centauri star system is the single most important collection of stars in the entire observable universe from humanity's perspective. Not because it is the biggest, not because it is the brightest, not because it has the most planets, but because it is the closest. And in the story of a species that dreams of reaching the stars, closeness is everything. Let me take you back. Way back. Thousands of years back. Imagine a human being, one of our ancient ancestors, standing on the plains of Africa or on the banks of the Nile or on the shores of the Mediterranean, looking up at the night sky. They did not have telescopes. They did not have spectrometers. They did not have mathematics sophisticated enough to measure the distance to a single star. All they had were their eyes and their wonder. And when they looked up, they saw points of light. Thousands of them. Some bright, some faint, some reddish, some bluish, some clustered together in a milky band across the sky, and they asked the most natural question a conscious being can ask when confronted with the unknown. What are those things? The Egyptians thought they were gods. The Greeks thought they were heroes placed in the heavens. The Babylonians thought they were messengers from the divine. Every civilization, every culture, every tribe that has ever existed on this planet has looked up at those points of light and told stories about them. But nobody for thousands and thousands of years could answer the simplest question of all: how far away are they? Think about that. For the vast majority of human history, we had no idea whether the stars were just above the clouds or infinitely far away. We did not know if they were small and close or enormous and distant. We did not know if they were fires or crystals or holes in a cosmic curtain. And then, slowly, over centuries, the answers began to come. Copernicus told us that the Earth was not the center of the universe. Galileo turned a telescope toward the sky and saw moons orbiting Jupiter, craters on our own moon, and phases of Venus, proving that the celestial realm was not perfect and unchanging, but dynamic and physical. Kepler figured out the mathematics of how planets orbit stars. Newton gave us gravity. And piece by piece, observation by observation, equation by equation, we built a picture of the cosmos that was staggering in its scope. And one of the most important realizations in that entire journey came when astronomers finally understood that our sun is a star. Just a star. One among billions. An ordinary, middle-aged, medium-sized yellow dwarf star sitting in an unremarkable part of an unremarkable galaxy. And if our sun is just a star, then every other star in the sky might be a sun. And if every star might be a sun, then every star might have planets. And if every star might have planets, then the number of possible worlds in the universe is not just large, it is incomprehensibly, mind-breakingly, soul-expandingly enormous. Hundreds of billions of stars in our galaxy alone, hundreds of billions of galaxies in the observable universe. The numbers become meaningless at that scale. They are too big for the human brain to process. But here is the thing. Knowing that there are billions of potential worlds out there is one thing. Actually finding them, actually seeing them, actually studying them, that is something else entirely. And for the longest time, that second part seemed impossible. Stars are so far away, and planets are so small and so faint compared to their parent stars, that the idea of detecting a planet orbiting another star seemed like pure fantasy. It would be like trying to see a firefly buzzing around a lighthouse, not from across a field, not from across a city, from across an ocean. That is the kind of challenge we are talking about. And yet, despite these seemingly insurmountable odds, in 1995, something miraculous happened. Two Swiss astronomers, Michel Mayor and Didier Queloz, using a telescope at the Haute-Provence Observatory in France, detected the very first planet orbiting a sun-like star beyond our solar system. The planet was called 51 Pegasi b, and it was nothing like anyone had expected. It was a gas giant, roughly half the mass of Jupiter, but it was orbiting its star in just 4 days. 4 days. For comparison, Mercury, the closest planet to our Sun, takes 88 days to complete one orbit. This new planet was so close to its star that its surface temperature was estimated at over 1,000 degrees Celsius. It was a world of hellfire, a gas giant baked to oblivion, and it shattered every model of planetary formation that existed at the time. Gas giants were supposed to form far from their stars, where it was cold enough for ices and gases to accumulate. Finding one practically kissing its star was like finding a snowman in a furnace. But that discovery, strange as it was, opened the floodgates. Once we knew it was possible to detect exoplanets, the race was on. The Kepler Space Telescope, launched in 2009, revolutionized everything. By staring at a single patch of sky containing about 150,000 stars, Kepler detected thousands of planets using the transit method, which involves watching for the tiny dimming of a star's light when a planet passes in front of it. Kepler showed us that planets are not rare, they are everywhere. Statistically, there are more planets in our galaxy than there are stars. Every star, on average, has at least one planet. Some have many more. And now, as of today, we have confirmed the existence of nearly 6,000 exoplanets. 6,000 worlds beyond our solar system. Some are rocky, some are gaseous, some are icy, some are in the habitable zone of their star, that sweet spot where liquid water could exist on the surface. Some orbit binary stars, some orbit pulsars, some are rogue planets, drifting through the darkness of interstellar space with no star at all. The diversity is staggering, and it has taught us something profound. Planetary systems are not neat, orderly places. They are wild, chaotic, unpredictable, and endlessly surprising. But here is the crucial point, the thing that brings us to the heart of today's story. Of all those nearly 6,000 exoplanets, the vast majority are very, very far away. Hundreds of light years. Thousands of light years. Some are so distant that their light has been travelling toward us since before the Roman Empire fell. We can detect them, yes. We can measure their mass and size and orbital period. In some cases, we can even analyse the composition of their atmospheres by studying the light that passes through them during a transit. But we cannot see them directly. We cannot take a photograph of their surface. We cannot study them in the kind of detail that would truly tell us what they are like. And that is why Alpha Centauri matters so much. Because at just 4.37 light-years away, it is the closest star system to our Sun. And closeness, in astronomy, means everything. It means better data. It means higher resolution. It means the ability to see things that are simply invisible at greater distances. If we are ever going to truly understand another planetary system, truly characterize its worlds, truly search for signs of life beyond Earth, the Alpha Centauri system is where we have the best chance of doing it. It is our cosmic next-door neighbour, and what happens at the house next door has always mattered more to us than what happens in a distant city. So let me tell you about this neighbour of ours. Let me tell you everything. Because to understand what James Webb found, you first need to understand the system it was looking at. Alpha Centauri is not one star, it is three. Three stars bound together by gravity, performing an intricate celestial dance that has been going on for over 5 billion years. The system sits in the constellation Centaurus, visible only from the southern hemisphere of Earth, and to the naked eye, the two brightest stars in the system appear as a single brilliant point of light, the third brightest star in the entire night sky, outshone only by Sirius and Canopus. Ancient mariners used it for navigation. Aboriginal Australians incorporated it into their Dreamtime stories. The people of the southern hemisphere have looked at that bright point of light for as long as there have been people in the southern hemisphere. But it was not until 1689 that a Jesuit priest named Father Jean Richaud, observing from Puducherry in India, discovered that this single point of light was actually two stars orbiting each other. And it was not until 1915 that a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa, discovered a third, much fainter companion lurking nearby. The first star, the brightest of the three, is called Alpha Centauri A, or Rigil Kentaurus. And if you were looking for a twin of our Sun, you could hardly do better than this. Alpha Centauri A is a G2V type star, which is the exact same spectral classification as our Sun. Let me repeat that because it is important. The exact same type. It has a mass of 1.08 solar masses, meaning it is about 8% heavier than our Sun. Its radius is 1.22 solar radii, making it about 22% larger. Its luminosity is 1.5 times that of our Sun, so it shines 50% brighter. Its surface temperature is 5,804 Kelvin, compared to our Sun's 5,778 Kelvin. Almost identical. Its age is estimated at 5.26 billion years, give or take about a billion, compared to our Sun's 4.6 billion years. It is slightly older, slightly bigger, slightly brighter, but in every fundamental way, it is our Sun's twin. If you plucked our Sun out of the Milky Way and placed it next to Alpha Centauri A, you would have trouble telling them apart. And this matters enormously. Because if we are looking for planets that might be similar to Earth, the best place to look is around stars that are similar to our Sun. The same type of star means the same type of habitable zone, the same type of radiation environment, the same type of conditions under which rocky planets can form and potentially develop liquid water on their surfaces. Alpha Centauri A is, in the most literal sense, the closest thing to our Sun that exists in our stellar neighbourhood. It is the most promising star in the sky for finding a world that might resemble our own. The second star is Alpha Centauri B, also known as Tollyman. This one is a bit smaller and cooler than both our Sun and Alpha Centauri A. It is a K1V type star with a mass of 0.91 solar masses, a radius of 0.86 solar radii, and a luminosity of about half that of our Sun. Its surface temperature is 5,207 Kelvin, making it noticeably cooler and more orange in colour compared to the yellow-white glow of Alpha Centauri A. But it is still a main sequence star, still fusing hydrogen in its core, still a perfectly respectable stellar citizen. Alpha Centauri A and B orbit each other in a dance that takes 79.76 years to complete. Their orbit is not circular but elliptical, with an eccentricity of 0.52. This means that the distance between them changes dramatically over the course of their orbit. At their closest approach, called periastron, they are only about 11.2 astronomical units apart, which is roughly the distance from our Sun to Saturn. At their farthest separation, called apastron, they are about 35.6 astronomical units apart, which is roughly the distance from our Sun to Pluto. This enormous variation in separation has profound implications for any planets that might exist in the system, because the gravitational influence of one star on the planets of the other changes dramatically depending on where the two stars are in their orbit. At periastron, the the gravitational perturbation is intense. At a pastron, it is much weaker. Any planet trying to maintain a stable orbit in this system has to contend with this constantly shifting gravitational landscape, and many possible orbits are simply unstable over billions of years. And then there is the third star, the runt of the litter, the smallest, faintest, and in many ways most interesting member of the trio, Proxima Centauri. This is a tiny red dwarf star, spectral type M5.5v, with a mass of only about 12% that of our Sun, and a luminosity so feeble that it produces less than 2/1000ths of our Sun's light output. You cannot see it with the naked eye. Even with a small telescope, it is a dim, unremarkable speck, but what it lacks in brightness, it makes up for in significance, because Proxima Centauri is the closest star to our Sun. Period at 4.2465 light-years, it is slightly closer than the Alpha Centauri A B pair, which sit at 4.344 light-years. Proxima Centauri orbits the A-B pair at an enormous distance of about 13,000 astronomical units, which is roughly 0.21 light-years. To put that in perspective, the entire orbit of Neptune around our Sun fits within about 30 astronomical units. Proxima Centauri is more than 400 times farther from Alpha Centauri A and B than Neptune is from our Sun. Its orbital period around the binary pair is estimated at roughly 547,000 years. That is so long that some astronomers have historically debated whether Proxima is truly gravitationally bound to the system at all, or whether it is simply passing by in a chance encounter. More recent measurements of its motion, however, strongly suggest that it is indeed bound, making it a true member of the triple system, albeit a very distant and lonely one. But Proxima Centauri has something that makes it absolutely fascinating despite its diminutive size. It has planets. Confirmed planets. The first was discovered in August 2016 by the European Southern Observatory, and it was announced with enormous fanfare. Proxima Centauri B, as it was named, is roughly Earth-sized, with a minimum mass of about 1.07 Earth masses. It orbits its star in just 11.2 days, at a distance of only 0.049 astronomical units, which is about 7.5 million kilometers. That sounds insanely close, and it is. But remember, Proxima Centauri is a tiny dim red dwarf. Its habitable zone, the region where liquid water could exist, is correspondingly close to the star, and Proxima B sits right in it. The discovery of an Earth-sized planet in the habitable zone of the nearest star to our Sun was electrifying. It dominated headlines around the world. Could there be life on Proxima B? Could there be oceans? Could it be our first destination when we finally develop interstellar travel? The possibilities seemed intoxicating, but as scientists studied the system more carefully, the picture became more complicated. Much more complicated. Proxima Centauri is what astronomers call a flare star. It is an angry, volatile little thing that periodically erupts with violent bursts of radiation, flares so intense that the star's brightness can increase by several times in a matter of minutes. These flares bombard any nearby planets with ferocious doses of ultraviolet and X-ray radiation, potentially stripping away their atmospheres and sterilizing their surfaces. Proxima B, sitting so close to this temperamental star, would bear the full brunt of these outbursts. Studies suggest that the radiation environment on Proxima B's surface could be hundreds of times more intense than anything experienced on Earth. Furthermore, Proxima B is almost certainly tidally locked to its star, meaning the same face always points toward Proxima Centauri, just as the same face of our Moon always points toward Earth. This would create a permanent day side, bathed in constant starlight, and a permanent night side, locked in eternal darkness. The temperature difference between the two hemispheres could be extreme, potentially making much of the planet uninhabitable. Whether a thick enough atmosphere could redistribute heat and moderate these extremes is still an open question, but the existence of such an atmosphere is itself uncertain, given the star's violent flaring. 2 more planets have been identified around Proxima Centauri since then. Proxima D, discovered in 2022, is a very small planet, only about 1/4 of Earth's mass, orbiting the star in just 5.1 days at a distance of only 0.029 astronomical units. It is far too close to the star and far too hot for liquid water. It is probably a bare rock, scorched and lifeless. Then there is Proxima C, a much more controversial candidate. Announced in 2019, it would be a mini Neptune about 7 times Earth's mass, orbiting at 1.5 astronomical units from the star, with a period of roughly 1928 days. But it orbits so far from the dim red dwarf that it would receive almost no warmth at all. It would be a frozen world if it exists, and its existence is still disputed. Some studies find evidence for it, others do not. It remains in scientific limbo. So that is the state of the Alpha Centauri system as it stood before Webb entered the picture. 3 stars. 3 confirmed or candidate planets around the smallest, dimmest star, and 0 confirmed planets around either of the 2 main Sun-like stars. 0. Despite decades of searching, despite multiple campaigns using the world's best telescopes and instruments, nobody had been able to definitively confirm a planet around Alpha Centauri A or Alpha Centauri B. It was not for lack of trying. In 2012, a team of astronomers announced the detection of an Earth-mass planet orbiting Alpha Centauri B with a period of just 3.24 days. The announcement made global headlines, but within a year, other researchers showed that the signal was almost certainly an artifact of the data analysis, a ghost in the noise. The planet was retracted, a humbling reminder of how difficult this game is. The 2 Sun-like stars of Alpha Centauri, the very stars most similar to our Sun, remained stubbornly planet-free as far as confirmed detections were concerned. And this is where the frustration lay. Here was the most important star system in the sky from the perspective of the search for other worlds, and the 2 stars most likely to host Earth-like planets had given us nothing. Proxima's planets were interesting, sure, but Proxima is a violent red dwarf, and its habitable zone is a harsh, radiation-blasted environment. If we wanted to find a world truly similar to Earth, orbiting a star truly similar to our Sun, at a distance close enough to actually study it in detail, Alpha Centauri A was the place to look. And nobody had managed to find anything there. Part of the problem is the binary nature of the system. Alpha Centauri A and B orbit so close to each other, at least relatively speaking, that their mutual gravitational influence makes planet detection incredibly difficult. The radial velocity method, which detects planets by measuring the tiny wobble they induce in their host star, gets confused by the much larger wobble induced by the binary companion. Sorting out the planetary signal from the binary signal is like trying to hear a whisper at a rock concert. The transit method does not help either, because the orbital inclination of any potential planet may not be aligned in a way that causes it to pass between us and its star. And direct imaging, actually taking a picture of the planet, was long considered essentially impossible for this system, because Alpha Centauri A is so bright, so close, and so complicated by the presence of its binary companion that no telescope had the precision to tease out the faint glow of a planet from the overwhelming glare of the stars. And then came James Webb. The James Webb Space Telescope is, by almost any measure, the most extraordinary scientific instrument ever constructed. It took over 25 years to design, build, test and launch. It cost approximately $10 billion, making it one of the most expensive scientific projects in history. It involved contributions from NASA, the European Space Agency, and the Canadian Space Agency, along with thousands of engineers, scientists, and technicians working in countries around the world. It was launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana, and it was deployed at the second Lagrange point, or L2, a gravitationally stable point about 1.5 million kilometers from Earth on the side opposite the Sun. There, shielded from the Sun, Earth and Moon by a tennis court-sized sun shield, that keeps it in permanent shadow. It operates at temperatures just a few dozen degrees above absolute zero, cold enough to detect the faintest whispers of infrared light from the most distant objects in the universe. Its primary mirror is 6.5 meters in diameter, composed of 18 hexagonal segments coated in gold, chosen because gold is an excellent reflector of infrared light. This mirror is nearly 3 times the diameter of the Hubble Space Telescope's mirror, giving it approximately 6 to 7 times the light-collecting area. It carries 4 main science instruments: the Near-Infrared Camera, or NIR-CAM, which is its primary imaging workhorse; the Near-Infrared Spectrograph, or NIRSpec, which can analyze the light from dozens of objects simultaneously; the Near-Infrared Imager and Slitless Spectrograph, or NIRIS, provided by Canada; and the Mid-Infrared Instrument, or MIRI, which operates at longer infrared wavelengths and is equipped with both a camera and a spectrograph. MIRI is the instrument that matters for our story. Built by a consortium of European institutions in partnership with NASA's Jet Propulsion Laboratory and the University of Arizona, MIRI operates in the mid-infrared range, from 5 to 28 micrometers. This wavelength range is crucial for exoplanet science, because while stars are brightest in visible light, planets, which are much cooler, emit most of their energy in the infrared. Think of it like a thermal camera. A star blazes in visible light like a bonfire, overwhelming everything around it. But in the infrared, the star is still bright, but the contrast between the star and a nearby planet is much smaller, perhaps 10,000 to 1 instead of 1 billion to 1 in visible light. This makes it potentially possible, with the right technology and the right technique, to detect the faint infrared glow of a planet even in the presence of its star's overwhelming brilliance. And MIRI has something else that makes it special for this purpose: coronagraphic masks. A coronagraph is a device that blocks the light of a star, allowing you to see fainter objects near it. The concept was invented in 1931 by the French astronomer Bernard Liot, who created it to study the sun's corona, the faint outer atmosphere that is normally invisible because the sun's disk is so much brighter. Modern coronagraphs are far more sophisticated. MIRI's coronagraphs use a technique called the 4-quadrant phase mask, which does not simply block the star's light physically, but manipulates the phase of the incoming light waves to create destructive interference, effectively cancelling out the starlight through wave physics. It is an elegant, almost magical technique that pushes the boundaries of what optics can achieve. But even with MIRI's coronagraph, observing Alpha Centauri was considered borderline insane by many in the astronomical community. The challenges were daunting. First, there was the brightness problem. Alpha Centauri A is the 3rd brightest star in the sky. Webb was designed to observe the faintest, most distant objects in the universe. Pointing it at one of the brightest stars is like using a night vision scope to look at the sun. The detectors could be overwhelmed, saturated, or damaged. Second, there was the binary problem. Even if you could block Alpha Centauri A's light with the coronagraph, Alpha Centauri B was right there next to it, flooding the field of view with its own bright light, creating artifacts and speckle patterns that could easily be confused with a planetary signal. Third, there was the motion problem. Alpha Centauri moves across the sky faster than almost any other bright star, with a proper motion of about 3.7 arc-seconds per year. Webb was designed to track slow-moving, or essentially stationary targets like distant galaxies. The operations team would have to develop entirely custom procedures to track this fast-moving system accurately. And yet, despite all of this, one man believed it was worth trying. His name is Charles Beichman, and he is an astronomer at NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute at Caltech's IPAC Astronomy Center. In 2017, years before Webb even launched, Beichman sent an email to colleagues proposing that they use Webb to search for planets around Alpha Centauri A. His opening line, as he later recalled, was essentially, "When you stop laughing, let's think about doing this project." He knew it sounded crazy. He knew the telescope was not designed for it. But he also knew that the potential payoff was enormous. If they could pull it off, they would be probing the habitable zone of the nearest sun-like star to Earth, something no telescope had ever been able to do with the power of direct imaging. Slowly, a team came together. Beichman was joined by Aniket Sanghi, a PhD student in astrophysics at the California Institute of Technology, who was looking for a challenging research project and found one that was, in his own words, one of the most challenging objects to work on. They were joined by Dmitry Mawet, also at Caltech, and a host of other collaborators. Together, they spent years developing the observational strategy, running simulations, planning every aspect of the observation with meticulous care. The key innovation, the breakthrough that made the observation possible, was a clever trick involving a reference star. Here is the problem they had to solve. When you put Alpha Centauri A behind the coronagraphic mask, you block most of its light, but the blockage is not perfect. Light diffracts around the edges of the mask, creating ripples and patterns in the surrounding image. These patterns are called speckle noise, and they look a lot like faint point sources, which is exactly what a planet would look like. So you have this confusing mess of speckle patterns, and somewhere in that mess there might or might not be a real planet. How do you tell the difference? One standard technique is called reference star differential imaging. You observe your target star with the coronagraph, and then you observe a different star, a reference star of similar brightness, with the same coronagraph setup. The speckle patterns from the coronagraph should be very similar for both stars, because they are produced by the telescope's optics, not by the stars themselves. So you can subtract the reference star image from the target star image, and the speckle patterns cancel out, leaving behind only real astronomical sources, like planets. But for Alpha Centauri, there was an extra complication: Alpha Centauri B. Even with A behind the coronagraph, B's light was contaminating the image. So the team found a particularly unremarkable star that they could use as a stand-in for B. By observing this reference star both centered on the coronagraph and off-center, they could model exactly how its light flowed through Webb's optics. This gave them a template that they could use to subtract out Alpha Centauri B's contamination from their images of Alpha Centauri A. It was painstaking work. Every detail had to be perfect. The pointing had to be exact. The timing had to be precise. The data processing had to account for dozens of potential artifacts and systematics. But in August 2024, the team was ready, and Webb turned its golden mirror toward the Alpha Centauri system. The raw data that came back was, predictably, a mess. Alpha Centauri A's partially blocked light created a complex pattern of diffraction spikes and speckles. Alpha Centauri B's light added another layer of confusion. The field was a chaotic tangle of overlapping light patterns, the kind of image that would make most astronomers throw up their hands in despair. But Beichman, Sanghi, and their team had spent years preparing for exactly this moment. Step by step, layer by layer, they peeled away the contamination. First, they subtracted the modeled light pattern from Alpha Centauri A itself. Then, using their reference star technique, they subtracted the contribution from Alpha Centauri B. Then they removed known instrumental artifacts, calibrated the residuals, and cleaned up the remaining noise. And when all of that was done, when all the starlight and all the artifacts and all the noise had been stripped away, something remained. A faint blob of light, sitting about 2 astronomical units from Alpha Centauri A, over 10,000 times fainter than the star itself. The team designated it S1 for Source 1. Now I want you to understand what this moment felt like for the scientists. Aniket Sanghi later described it this way: as a direct imager, you're always confounded by artifacts. You're very skeptical of anything you see, but this one just popped out so clearly. When you spend your career staring at messy, noisy data, looking for signals that might not be there, and something just pops out at you with a clarity that makes your breath catch, that is a special moment. That is the moment every astronomer lives for. But scientists are trained to be their own harshest critics. The team did not celebrate. They did not rush to publish. Instead, They tried everything they could think of to prove that S1 was not a planet. Could it be a background galaxy? They checked. The position did not match any known galaxies, and besides, a background galaxy would appear stationary while Alpha Centauri moved across the sky, so follow-up observations could rule that out. Could it be a passing asteroid? The brightness profile was wrong, and the motion pattern did not match any known asteroid trajectories. Could it be a detector glitch or an artifact of the electronics? The signal appeared in the data in a way that was consistent with a real astronomical source, not with any known instrumental effect. Could it be a speckle of residual starlight that had somehow survived the subtraction process? They modelled every predicted speckle pattern, and none of them matched the position or brightness of S1. Nothing they tried could explain S1 as anything other than a real object. And its properties, its brightness in the mid-infrared, its position relative to the star, its apparent separation, all pointed toward the same conclusion: it was consistent with being a planet. A gas giant, approximately the mass of Saturn. Orbiting Alpha Centauri A at a distance of about 2 astronomical units. But one observation is never enough in science. You never hang your hat on a single data point. The history of astronomy is littered with premature announcements that turned out to be wrong, signals that turned out to be noise, planets that turned out to be phantoms. The team knew they needed confirmation. They needed to see S1 again, ideally at a different time, to verify that it was a persistent, real object and not some transient artifact. And this is where the story takes a dramatic and unexpected turn. Because when the team applied for additional telescope time, was granted director's discretionary time, which is a special allocation reserved for urgent and time-sensitive observations, and turned Webb back toward Alpha Centauri A in February 2025, they found something that nobody expected. S1 was gone. The exact position where the planet candidate had been seen just 6 months earlier was empty. The team repeated their entire observation procedure, used the same instrument, the same coronagraph, the same data processing pipeline. Everything was the same, and the result was a blank. No signal, no blob, nothing. They tried again in April 2025. Same result. Nothing. S1 had vanished. Imagine the feelings in that team room. Months of preparation, years of planning. A detection that seemed so clear, so promising, so potentially transformative. And now it was gone. Was it an artifact after all? Had they been fooled by some subtle systematic error that they had failed to account for? Had the most exciting discovery in exoplanet science in years just evaporated into nothing? Many research teams might have given up at that point. They might have quietly shelved the result, marked it as a possible artifact, and moved on to other projects. But Beichman, Sanghi and their colleagues are not the giving up type. Instead of despairing, they asked a different question. If S1 is a real planet, where could it have gone? Why would a planet be visible in August 2024, but invisible in February and April 2025? And the answer, when they found it, was both simple and profound. The team built computer models to simulate millions of potential orbits for a hypothetical planet around Alpha Centauri A. They incorporated everything they knew: the position and brightness of S1 in August 2024, the non-detection in February 2025, the non-detection in April 2025, and a crucial additional piece of information that I have not yet mentioned: a 2019 observation from a ground-based telescope that had shown a tantalizing but inconclusive signal in a similar location. Let me tell you about that 2019 observation, because it adds a fascinating layer to this story. In 2019, a team of astronomers used the NEAR experiment on the European Southern Observatory's Very Large Telescope in Chile, specifically designed to search for planets in the Alpha Centauri system, to observe Alpha Centauri A in the mid-infrared. They detected a faint thermal signal near the star. It was ambiguous. It could have been a planet, or it could have been a clump of warm dust, or it could have been an instrumental artifact. The result was published in Nature Communications in 2021, but it was presented cautiously, without a definitive claim of a planetary detection. It was a hint, nothing more. But here is the remarkable thing. The position of that 2019 hint was consistent with the position of S1 in the 2024 Webb data. 2 different telescopes, 2 different instruments, 2 different observation epochs separated by 5 years, and both pointing to the same location near Alpha Centauri A. So the team fed all of this into their simulation: the 2019 Wilt hint, the 2024 Webb detection, the 2025 non-detections. And they added one more constraint. Any plausible orbit had to be gravitationally stable in the presence of Alpha Centauri B. Because the binary companion exerts a powerful gravitational influence on anything orbiting Alpha Centauri A, many potential orbits are simply unstable over billions of years. A real planet would have to be on an orbit that can survive the constant gravitational tugging from the companion star without being flung out of the system or crashing into the star. The simulations ran millions of possible orbits, and the result was striking. In approximately half of all simulated orbits that were consistent with the 2024 detection, the planet would have moved too close to Alpha Centauri A by February and April 2025 to be detectable by Webb's coronagraph. Here is why. The planet's hypothetical orbit is not circular, but elliptical, carrying it between about 1 and 2 astronomical units from the star. When the planet is at the outer part of its orbit, around 2 astronomical units, it is far enough from the star for the coronagraph to separate its light from the star's glare. But when it swings in to the inner part of its orbit, around 1 astronomical unit, it gets too close to the star, and its faint light is swallowed up by the star's residual glare even with the coronagraph engaged. In other words, the planet did not disappear. It did not cease to exist. It simply moved to a part of its orbit where Webb could not see it, hidden in the overwhelming brightness of its star at close range. Aniket Sanghi explained it this way: we found that in half of the possible orbits simulated, the planet moved too close to the star and wouldn't have been visible to Webb in both February and April 2025. The disappearance, far from disproving the planet, was actually consistent with the planet hypothesis. A planet on an elliptical orbit would naturally spend part of its time too close to the star to be seen. The non-detections were not evidence against the planet. They were evidence that the planet's orbit is eccentric, which actually fits perfectly with the 2019 and 2024 detections. This is the beauty of science. What initially looked like a failure, a frustrating non-result, turned out to be a clue. The disappearing planet was not a mystery to be mourned, but a puzzle to be solved. And when the team solved it, the picture that emerged was more compelling than ever. Based on the brightness of S1 in the mid-infrared, the constraints from the 2019 Volt observation, the non-detections in 2025, and the requirement for orbital stability in the binary system, the team constructed a profile of the candidate planet. If it is real, and that remains an if for now, here is what it looks like. Alpha Centauri A, as it would be designated if confirmed, is a gas giant approximately the mass of Saturn, which is about 95 times the mass of Earth. It orbits Alpha Centauri A on an elliptical path with a semi-major axis somewhere between 1 and 2 astronomical units, giving it an orbital period of roughly 1.5 to 2.5 Earth years. Its temperature is similar to the giant planets in our own solar system, warmer than our Saturn but much cooler than the scorching hot Jupiters that have been found around other stars. It is not a rocky world. It is not a place where you could stand on a surface and look up at an alien sky. It is a ball of gas, mostly hydrogen and helium, with thick atmospheric layers and crushing pressures deep in its interior. And here is the fact that makes this candidate truly extraordinary. It orbits within the habitable zone of Alpha Centauri A. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where the temperature is just right for liquid water to exist on the surface of a planet. Not too hot so the water boils away, not too cold so it freezes solid. Just right, For Alpha Centauri A, which is slightly brighter than our Sun, the habitable zone extends from roughly 1.2 to about 2.5 astronomical units. The candidate planet's orbit, varying between 1 and 2 astronomical units, sits right in this sweet spot. If this planet is confirmed, it will be the closest planet to Earth that orbits within the habitable zone of a Sun-like star. Let me say that again, because it deserves to sink in. The closest habitable zone planet around a Sun-like star ever found by anyone at just 4.37 light years. That is historically unprecedented. That is paradigm shifting. That is the kind of discovery that gets carved into the bedrock of astronomical history. But I know what you are thinking, because I was thinking the same thing when I first read the research. If it is a gas giant, what good is a habitable zone? Gas giants do not have solid surfaces, they do not have oceans, they do not have landscapes where life could take root. A Saturn-mass planet sitting in the habitable zone is like having a perfect piece of beachfront property, but building a chemical factory on it. The location is ideal, but the thing itself is all wrong for life as we know it. And you would be right to think that, if we only considered the planet itself. But we must think bigger. We must think about moons. In our own solar system, some of the most promising places for life are not planets at all. They are moons. Jupiter's moon Europa has a subsurface ocean of liquid water beneath a shell of ice kept warm by tidal heating from Jupiter's immense gravity. Saturn's moon Enceladus shoots geysers of water vapor and organic molecules into space from its own subsurface ocean. Saturn's largest moon, Titan, has a thick nitrogen atmosphere, complex organic chemistry, and lakes of liquid methane and ethane on its surface. These moons are alive with possibility, and they orbit gas giants, not small rocky planets. Now imagine Alpha Centauri A, a Saturn-mass gas giant orbiting in the habitable zone of a Sun-like star. If it has large moons, and gas giants in our solar system universally have large collections of moons, those moons would be in the habitable zone too. But unlike Europa and Enceladus, which are in the outer solar system where sunlight is feeble and life depends on tidal heating alone, moons of Alpha Centauri A would be bathed in comfortable levels of starlight from Alpha Centauri A, the same intensity of light that Earth receives from our Sun. They would have both tidal heating from the gas giant and solar energy from the star. They would have multiple energy sources for any potential biosphere. In 2018, researcher Ren Heller proposed that exomoons around gas giants in the habitable zones of Sun-like stars could be what he called superhabitable, meaning they could potentially offer even more favourable conditions for life than Earth itself. The combination of tidal energy, stellar energy, and a protective magnetic field of a large gas giant could create environments where life not only could exist, but could thrive. And here is where science fiction and scientific reality converge in a way that is almost spooky. In James Cameron's Avatar films, the lush jungle moon of Pandora orbits a gas giant called Polyphemus in the Alpha Centauri A system. When Cameron created that fictional setting, he chose Alpha Centauri A specifically because it was the nearest Sun-like star. He imagined a habitable moon around a gas giant because he was inspired by the scientific speculation about such worlds. And now, decades later, Webb may have found something eerily similar: a gas giant in the habitable zone of Alpha Centauri A. Fiction may not have predicted reality, but it resonated with it in a way that is deeply satisfying. Scientists are already exploring this possibility. In September 2025, a paper was published on astrobiology.com titled "Seeking the Worlds of Avatar: Prospects for Detecting Moons Orbiting a Giant Planet in Alpha Centauri A's Habitable Zone." The paper presents a simulation framework for investigating the possibilities of detecting exomoons via their astrometric signal, the tiny wobble they would induce in the planet as they orbit it. Detecting such moons is far beyond the capability of any current telescope, but the fact that scientists are already thinking about it, already running simulations, already developing theoretical frameworks, tells you everything you need to know about how exciting this discovery is. But let me be honest with you, because honesty is as important as excitement in science. We do not know if Alpha Centauri A has moons. We do not even know if Alpha Centauri A exists. What we have right now is a candidate, a very strong, very compelling candidate, backed by multiple lines of evidence and consistent with extensive computer modelling, but still a candidate. It has not been confirmed. And until it is confirmed by additional observations, it remains possible. However unlikely that S1 was some kind of artifact or astrophysical false positive that the team failed to identify. Elizabeth Matthews, an exoplanet-focused astrophysicist at the Max Planck Institute for Astronomy in Heidelberg, Germany, who was not involved in the research, put it perfectly: if it's real, it's amazing. It's a really exciting candidate, quite an intriguing candidate. The authors work hard to make a case for why this, frankly, small and faint blob of light is believable, but I think there are still some open questions that need to be answered to really be 100% sure. And Emily Rickman, a European Space Agency astronomer at the Space Telescope Science Institute who also was not involved, added an important perspective. All data, whether it's a detection or not, tells you something. Even if this ultimately is a non-detection and the planet candidate is something else, I think it's a really important paper in understanding the true capabilities that JWST's MERI can push to. And I think that's just as important. This is science operating at its best. Cautious but bold, skeptical but excited, honest about uncertainty, while still daring to imagine what might be true. The team behind this discovery did not oversell their result. They presented it for what it is: strong evidence, not proof. And they laid out exactly what needs to happen next to either confirm or refute their finding. So what does need to happen next? The answer, in a word, is more observations. The team's orbital simulations have identified the next window of opportunity. Based on the best fit orbits consistent with all the available data, August 2026 is the most promising time for the planet to be once again at a favourable position in its orbit, far enough from Alpha Centauri A to be separated from the star's glare by Webb's coronagraph. The team is applying for telescope time to observe the system again at that window. If they see S1 again, at the position predicted by their orbital models, that would be extraordinarily compelling evidence for a real planet. If they do not see it, the planet hypothesis would be significantly weakened, though not necessarily ruled out, since the planet could be on an orbit that keeps it hidden for longer than the models predict. Because what happens when Webb looks at Alpha Centauri again could be one of the most significant moments in the history of exoplanet science. If the planet is confirmed, it will immediately become the most important target in the sky for every telescope on Earth and in space. If it is not confirmed, the search will continue, because the Alpha Centauri system remains the most valuable real estate in the sky for planet hunters, regardless of the outcome of this particular candidate. But Webb is not the only telescope that will be able to study this system. There are more coming, and they are powerful. NASA's Nancy Grace Roman Space Telescope, named after the legendary astronomer who is often called the Mother of Hubble for her role in championing the Hubble Space Telescope, is set to launch by May 2027 and potentially as early as fall 2026. Roman is a different beast from Webb. Its primary mirror is smaller, only 2.4 meters compared to Webb's 6.5 meters, so it collects less light. But it carries a piece of technology that Webb lacks: a purpose-built, state-of-the-art coronagraph instrument, or CGI, that represents a quantum leap in starlight suppression technology. Unlike Webb's coronagraph, which uses relatively simple masks to block starlight, Roman's coronagraph uses deformable mirrors, flexible mirrors whose surfaces can be adjusted in real time, pixel by pixel, to create what astronomers call a dark hole in the image, a region where starlight is suppressed by factors of 1 billion or more. This is achieved through a process called wavefront control, where the instrument continuously measures the incoming light and adjusts the mirror shape to cancel out the star's light through destructive interference. It is like noise-cancelling headphones for light. Roman's coronagraph operates in visible and near-infrared wavelengths, which complements Webb's mid-infrared observations perfectly. If the Alpha Centauri planet is observed by both telescopes, the combination of infrared and visible light data would yield an unprecedented wealth of information. The infrared data from Webb tells us about the planet's temperature and thermal emission. The visible light data from Roman would tell us about the planet's size, its reflectivity, how much starlight it bounces back, and potentially the composition of its upper atmosphere. Together, the two telescopes would give us a more complete picture of an exoplanet than we have ever had for any world beyond our solar system. And Roman was specifically designed with binary star systems like Alpha Centauri in mind. Its advanced coronagraph can handle the complexity of multiple bright sources in the field of view, something that Webb's simpler coronagraph struggles with. This makes Roman ideally suited for follow-up observations of Alpha Centauri A, if it is confirmed. Beyond Roman, the next decade will see the completion of a new generation of ground-based telescopes that will push the boundaries of what is possible in exoplanet science. The European Extremely Large Telescope, or ELT, currently under construction in Chile's Atacama Desert, will have a primary mirror 39 meters in diameter, nearly 6 times the diameter of Webb's mirror. When it sees first light around 2028, it will be the largest optical and near-infrared telescope ever built, and its extreme adaptive optic systems will allow it to correct for atmospheric turbulence with such precision that it could potentially directly image rocky planets around nearby stars, not just gas giants, but Earths. The 30-meter telescope and the giant Magellan telescope, also under development, will provide similar capabilities. The convergence of these technologies, Webb's infrared power, Roman's advanced coronagraph, the ELT's sheer collecting area and spatial resolution, creates a toolkit that is unprecedented in the history of astronomy. Within the next decade, we will have the ability to study the Alpha Centauri system in a level of detail that previous generations of astronomers could only dream of. We will be able to search for smaller planets, potentially rocky ones, in the habitable zones of both Alpha Centauri A and B. We will be able to characterize the atmospheres of any planets we find, looking for signatures of water vapor, carbon dioxide, methane, and possibly even oxygen or ozone, which could be indicators of biological activity. We will be able to look for moons around gas giants, search for rings, study the dynamics of planetary orbits in the binary system, and piece together the complete story of how this remarkable star system formed and evolved over 5 billion years. But I want to take this even further, because the story of Alpha Centauri is not just about telescopes and data. It is about the deepest aspiration of our species, to go there. From the moment humans first understood that the stars were other suns at unimaginable distances, the dream of traveling to them has captured our imagination. Science fiction is built on this dream. Star Trek, Star Wars, Foundation, Interstellar, The Expanse, Three-Body Problem, all of them, in one way or another, are about humanity reaching beyond the cradle of our solar system and touching the stars. And the star we always talk about reaching first is Alpha Centauri. But the distances involved are almost incomprehensible. 4.37 light years, that is about 41.3 trillion kilometers. Let me try to make that number real for you. If you got into a car and drove at 100 kilometers per hour without stopping, it would take you 47 million years to reach Alpha Centauri. If you took the fastest commercial airplane, traveling at about 900 kilometers per hour, it would take about 5 million years. If you hitched a ride on the International Space Station, traveling at 28,000 kilometers per hour, it would take about 160,000 years. If you rode along with the Voyager 1 spacecraft, currently the fastest human-made object leaving the solar system at about 61,000 kilometers per hour, it would take about 73,000 years. Even the Parker Solar Probe, which is its closest approach to the Sun, reaches speeds of about 700,000 kilometers per hour. The fastest speed ever achieved by a human-made object would take about 6,300 years to cover the distance to Alpha Centauri if it could maintain that speed, which it cannot, because it only reaches that speed during its closest solar flybys. Chemical rockets, the technology that took us to the moon and built the International Space Station, are simply not capable of interstellar travel on any timescale meaningful to a human civilization. We need something fundamentally different. We need a new paradigm in propulsion, and that is exactly what a project called Breakthrough Starshot proposes to provide. Announced on April 12, 2016 by the Russian-Israeli billionaire Yuri Milner, with the endorsement of the late Stephen Hawking and support from Mark Zuckerberg, Breakthrough Starshot is a $100 million research and engineering program aimed at developing the technology for humanity's first interstellar mission. The destination: the Alpha Centauri system. The timeline: a launch within a generation. The method: light sails. The concept is elegantly simple in principle and diabolically complex in execution. Here is how it works. You build a very small spacecraft called a starship, weighing about 1 gram. Yes, 1 gram. About the weight of a paperclip. This tiny spacecraft contains a miniature camera, a miniature communication system, a tiny onboard computer, navigation sensors, and a power source, all compressed into a chip a few centimeters across. Modern advances in nanotechnology and microelectronics make this conceivable, though not yet practical. You attach this star chip to a light sail, an ultra-thin, highly reflective sheet of material a few meters across. The sail does not catch wind, like the sails on a ship. It catches light. Specifically, it catches photons from a powerful laser. On the ground, you build an enormous laser array, a phased array of thousands of individual lasers synchronized to produce a single coherent beam with a combined power of about 100 gigawatts. That is more power than the entire electricity production of some small countries, concentrated into a single beam of light. You fire this laser at the light sail for about 10 minutes, and the pressure of the photons accelerates the sail and its tiny starship payload to astonishing speeds, 15 to 20% of the speed of light. At 20% of light speed, the starship would be traveling at about 216 million kilometers per hour. At that speed, it would reach Alpha Centauri in approximately 20 years. Upon arrival, it would fly through the system at high speed, since it has no way to slow down, taking photographs, collecting data, and making measurements during its brief flyby. It would then use a tiny onboard laser to transmit that data back to Earth. The data, traveling at the speed of light, would take about 4.4 years to arrive, so the total time from launch to receiving data would be about 24 to 25 years. That is within a human lifetime. Within a single generation. The first close-up images of another star system, another set of planets, another potential home for life, could be seen by people who are alive today. But the technical challenges are formidable. Building a 1-gram spacecraft that can survive in space and function autonomously is an extraordinary engineering challenge. The light sail must survive the incredible forces of acceleration during the 10-minute laser push, about 60,000 times the force of gravity. At 20% of light speed, even a tiny grain of interstellar dust would hit the sail with the impact energy of a small bomb, so the sail must be designed to survive these impacts or be made of a material that self-heals or that the mission can tolerate some damage to. The laser array itself, 100 gigawatts of synchronized laser power, is far beyond anything that exists today. The pointing accuracy required is mind-boggling. The laser must remain focused on a sail that is getting farther away every second, and the beam must be coherent over distances of millions of kilometers. These are not minor engineering hurdles. They are monumental technological challenges that will require breakthroughs in material science, laser technology, computational systems, and space engineering. But the Breakthrough Starshot team believes that none of these challenges violates any known law of physics. They are engineering problems, not physics problems. And engineering problems, given enough time, money, and ingenuity, can be solved. There are other interstellar travel concepts as well, each with its own blend of promise and impracticality. Nuclear pulse propulsion, conceived in the 1950s and 1960s under Project Orion, proposes detonating nuclear bombs behind a spacecraft to accelerate it. It is brutal but effective, at least in theory, and could potentially reach 5 to 10% of the speed of light. Fusion propulsion, envisioned by the British Interplanetary Society's Project Daedalus in the 1970s and updated by Project Icarus, would use a miniature fusion reactor on the spacecraft to achieve similar speeds. Antimatter propulsion, the holy grail of rocket propulsion, uses the annihilation of matter and antimatter to produce energy with 100% efficiency. But we can currently produce only nanograms of antimatter per year, and containing it is an unsolved problem. And then there are generation ships, massive spacecraft carrying thousands of people on a journey lasting hundreds of years, where multiple generations would live and die en route, arriving at Alpha Centauri centuries after departure. Each of these concepts has its enthusiasts and its skeptics. None is practical with today's technology. But the fact that serious scientists and engineers are studying them, modeling them, testing component technologies, and publishing peer-reviewed papers about them is a sign that interstellar travel has moved from the realm of pure fantasy into the realm of long-term engineering planning. We are not there yet. We may not be there for decades or even centuries, but the path is being mapped. And every discovery, like the potential planet around Alpha Centauri A, adds urgency and motivation to that mapping. Because now there might be something specific to go look at. Not just a star, not just an abstract destination. A planet. In the habitable zone. Possibly with moons, possibly with water, possibly with who knows what. This brings us to the question that has been lurking beneath the surface of this entire discussion, the question that drives more astronomical research than any other. The question that haunts the human imagination like nothing else. Could there be life? Let me address this carefully and honestly, because the temptation to speculate wildly is enormous, and the duty to stay grounded is even greater. Could there be life on Proxima Centauri B? It is in the habitable zone. It is roughly Earth-sized. It could have a rocky surface. In theory, liquid water could exist there. But the environment is harsh. The flares from Proxima Centauri are vicious, releasing bursts of radiation that could strip away any atmosphere and sterilize the surface. The planet is almost certainly tidally locked, with one face in eternal daylight and the other in eternal darkness. The temperature extremes could be severe. If there is life there, it would have to be tough, adapted to conditions far more extreme than anything on Earth. Extremophile organisms, perhaps, clinging to existence in underground shelters or in the twilight zone between the sunlit and dark hemispheres. Possible? Yes. Likely? We simply do not know. The James Webb Space Telescope has been attempting to detect an atmosphere on Proxima b by looking for carbon dioxide absorption features in the mid-infrared. But the results so far have been inconclusive. The data is noisy, the signal is faint, and different analyses reach different conclusions. We are at the very edge of what current technology can measure. Could there be life on the hypothetical moons of Alpha Centauri A, if the planet and its moons exist? As we discussed, the moons would be in the habitable zone, receiving both stellar energy from Alpha Centauri A and tidal energy from the gas giant. If they are large enough to hold atmospheres, they could have conditions favourable for liquid water. The scenario is not implausible. In our own solar system, Europa and Enceladus have demonstrated that liquid water can exist on moons far from the sun's warmth, sustained by tidal heating alone. A moon in the habitable zone of a sun-like star, with additional tidal heating, could be an even more promising environment. But we must be careful here. The existence of conditions favourable for life is not the same as the existence of life. Life requires not just water and energy, but a complex chain of chemical events that we still do not fully understand. The origin of life on Earth is one of the deepest unsolved problems in science. We know it happened, because we are here, but we do not know exactly how, or how likely it was, or how often it might happen elsewhere. The famous Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction on which life actually develops, the fraction that develops intelligence, the fraction that develops technology capable of communication, and the length of time such civilizations survive. The problem is that most of these factors are unknown, and the estimates span an enormous range from 0, meaning we are alone, to millions, meaning the galaxy is teeming with civilizations. What the potential discovery around Alpha Centauri A does is nudge one of those factors in a very interesting direction. If a habitable zone planet exists around the very nearest Sun-like star to our own, then habitable zone planets around Sun-like stars must be extremely common. The probability that the nearest one just happens to be the only one is vanishingly small. If it is there, then they must be everywhere, billions of them in our galaxy alone. And if habitable worlds are everywhere, then the chances of life developing on at least some of them go up significantly. We are not saying that life exists on Alpha Centauri A or its moons. We are not even saying that the planet exists for certain. What we are saying is that the universe appears to be providing the conditions for life in abundance, right next door. And that by itself is a profound statement about the nature of the cosmos we inhabit. Let me also take a moment to discuss something that often gets overlooked in the excitement over individual discoveries. What this detection tells us about the capabilities of our instruments and the ingenuity of our species. The fact that JWST, a telescope designed to look at the faintest and most distant objects in the universe, was successfully repurposed to observe one of the brightest and closest stars in the sky, is a testament to human adaptability and engineering brilliance. The operations team at the Space Telescope Science Institute had to develop entirely new observing sequences. The science team had to invent new data processing techniques. PhD students like Aniket Sanghi had to push the boundaries of existing methods and develop new ones. And they did it. They took a tool designed for one purpose and used it for something completely different, pushing it far beyond its designed capabilities, and got a result that nobody was certain was possible. This matters because it sets a precedent. If Webb can do this for Alpha Centauri A, it can potentially do it for other nearby stars. The techniques developed by Beichman, Sanghi and their team are not one-time tricks. They are methodologies that can be applied to future observations of other star systems, progressively pushing the frontier of what direct imaging can achieve. Every great scientific advance opens doors to further advances, and this observation has kicked open a door that many thought was locked shut. Pierre-Olivier Lagage, a French scientist who was a co-author on the papers and was the French lead for the development of MIRI, captured this sentiment beautifully. These are some of the most demanding observations we've done so far with MIRI's coronagraph. When we were developing the instrument, we were eager to see what we might find around Alpha Centauri. And I'm looking forward to what it will reveal to us next. What it will reveal next. That is the key phrase. This is not an ending. This is a beginning. Now let me step back from the technical details and the observational specifics and talk about what this discovery, if confirmed, means in a broader sense, because the significance of finding a planet in the habitable zone of Alpha Centauri A extends far beyond the boundaries of astronomy. It touches on philosophy, culture, the human condition, and our collective future as a species. For as long as we have been conscious beings, we have grappled with a single, terrible, beautiful question. Are we alone? Is this planet, this pale blue dot hanging in the void, the only place in the universe where matter has arranged itself into patterns complex enough to contemplate its own existence? Are we the universe's only way of knowing itself? Or is the cosmos teeming with life, with minds, with civilizations, perhaps some far older and wiser than our own? We do not have the answer. We may not have it in our lifetimes. But every discovery like this one, every habitable zone planet we find, every atmosphere we characterize, every biosignature we search for, brings us incrementally, agonizingly, thrillingly closer to the truth. And the fact that these discoveries are happening at an accelerating pace, that we are finding more and more worlds, with more and more sophisticated instruments in more and more promising configurations, suggests that we are approaching a threshold. A moment in human history when we might, for the first time, be able to say definitively whether or not life exists beyond Earth. That moment has not arrived. But it feels closer than it has ever been, and the Alpha Centauri system, our nearest neighbour, is at the centre of that convergence. Think about what it would mean. Think about the moment when a scientist stands at a podium and announces with confidence that we have detected unambiguous signs of biological activity on a world orbiting another star. The implications would be staggering. Every religion, every philosophy, every worldview would have to grapple with the knowledge that we are not unique, that life is a universal phenomenon, that the cosmos is not a cold, dead expanse, but a living, breathing, evolving entity of which we are just one small part. It would be the most important discovery in the history of our species. Bar none, more significant than fire, more significant than the wheel, more significant than the printing press or the internet or nuclear energy. The knowledge that we are not alone would fundamentally reshape what it means to be human. And even if we never find life, even if every world we examine turns out to be sterile, that too would be profoundly significant. It would mean that whatever happened on Earth, whatever chain of events led from chemistry to biology, from inanimate matter to living cells, was so improbable, so extraordinary, so miraculous in the truest sense of the word, that it happened only once in the entire observable universe. And that would make us, and every living thing on this planet, from the humblest bacterium to the most complex human brain, infinitely precious. The only sparks of consciousness in a vast, unconscious cosmos. What a responsibility that would impose. What a motivation to protect and cherish the life we have. Either way, the answer changes everything. And the path to that answer runs through Alpha Centauri. Let me bring us back to the present moment and the specific scientific reality of what we know and do not know right now in mid-2026. The two papers describing the JWST detection of the Alpha Centauri A candidate were announced on August 7, 2025, and have been accepted for publication in the Astrophysical Journal Letters, one of the most prestigious journals in astrophysics. The lead authors are Charles Beichman of NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute at Caltech's IPAC, and Aniket Sanghi, a PhD student at the California Institute of Technology. The research involved observations from August 2024, February 2025, and April 2025 using JWST's MIRI instrument with its coronagraphic mask. The candidate planet S1 was detected in the August 2024 observation at a separation of approximately 2 astronomical units from Alpha Centauri A, over 10,000 times fainter than the star. It was not detected in the February 2025 or April 2025 follow-up observations. Computer simulations of millions of possible orbits showed that approximately half of all plausible orbits would result in the planet being too close to the star to be detected by Webb's coronagraph at the times of the follow-up observations. The candidate is consistent with a gas giant approximately the mass of Saturn, orbiting in an elliptical path varying between 1 and 2 astronomical units from the star, with an orbital period of 1.5 to 2.5 years. A previous, inconclusive detection from the European Southern Observatory's Very Large Telescope in 2019 is consistent with the same object, providing additional, independent support for the planet hypothesis. The scientific community's response has been cautiously excited. Experts who were not involved in the research have praised both the ambition of the observation and the rigor of the analysis, while noting that confirmation through additional observations is essential. The next favourable observing window is expected in August 2026, and the team is seeking telescope time for that critical observation. If confirmed, the planet would be the closest to Earth that orbits in the habitable zone of a Sun-like star, and it would represent a new milestone for direct imaging of exoplanets, being the closest to its host star of any directly imaged planet. It would challenge existing models of planetary formation in binary star systems and open new avenues of research into the possibility of habitable moons. Now let me take a different angle on this story and explore something that we have touched on, but not fully developed. The challenge of planet formation in binary star systems, and what the existence of Alpha Centauri A would tell us about the physics of how planets are born. In our own solar system, which has a single star, planet formation followed a relatively neat pattern. The Sun formed from a collapsing cloud of gas and dust about 4.6 billion years ago. The leftover material formed a disk around the young Sun, called the protoplanetary disk. Close to the Sun, where temperatures were high, only metals and silicates could condense, leading to the formation of small, rocky planets: Mercury, Venus, Earth and Mars. Farther out, beyond the snowline where water and other volatiles could freeze into ice, the solid material was much more abundant, allowing the cores of giant planets to grow large enough to capture hydrogen and helium gas from the disk, forming the gas giants Jupiter and Saturn and the ice giants Uranus and Neptune. This model, called the core accretion model, works beautifully for our solar system, but it was developed for a single star system. In a binary system like Alpha Centauri, things are much more complicated. The gravitational influence of the companion star disrupts the protoplanetary disk, potentially preventing it from extending to large distances, truncating it, stirring it up, and making it much harder for planets to form. Computer simulations of planet formation in the Alpha Centauri system suggest that the protoplanetary disk around each star would have been truncated to a radius of about 2 to 3 astronomical units by the gravitational influence of the other star. This is much smaller than the disk in our solar system, which extended to at least 30 astronomical units. With a smaller disk, there is less material to work with, and the dynamic environment makes it harder for planetesimals to grow through collisions without being disrupted. Despite these difficulties, most simulations do predict that rocky planets could form around both Alpha Centauri A and B, particularly in the inner regions of the disk, where the companion star's influence is weakest. Some simulations even produce Earth-mass planets in the habitable zone. But gas giants are a different story. Forming a Saturn-mass gas giant requires accumulating a large solid core first, and then capturing a massive envelope of gas. In the truncated, dynamically hot disk of a binary system, this is much harder to achieve. So if Alpha Centauri A is real, it is telling us that gas giant formation is possible in closer binary systems than we previously thought. Or perhaps the planet formed farther out and migrated inward, pushed by gravitational interactions with the disk or with other planets or with the companion star. Or perhaps it was captured, having formed elsewhere and been drawn into Alpha Centauri A's orbit by some chance gravitational encounter. Each of these possibilities has different implications for our understanding of planet formation physics, and confirming the planet's existence would allow theorists to test these scenarios against the observational constraints. But there is a darker implication as well. Jason Wang, an astronomer at Northwestern University who specializes in direct imaging of exoplanets, pointed out something important about what a gas giant on an eccentric orbit in the habitable zone would mean for the prospects of finding an Earth-like planet in the same system. Our solar system is a very quiescent, nicely structured system, Wang said. There's all the small planets closer in, all the big planets further out. We're almost all on circular orbits. It's very nice and peaceful. Alpha Centauri A, if it has a Saturn-mass planet ploughing through its habitable zone on an eccentric orbit, is not peaceful at all. It is chaotic. And a gas giant on an eccentric orbit is like a cosmic wrecking ball. As it swings in and out through the habitable zone, its gravity would perturb the orbits of any smaller planets, potentially scattering them out of the system entirely, or crashing them into the star, or pushing them into orbits so eccentric that they become uninhabitable. the chances of a small, rocky, Earth-like planet surviving in the habitable zone of Alpha Centauri A alongside this gas giant are slim to none. This is a sobering thought. For decades, Alpha Centauri A, being the nearest Sun-like star, has been the primary focus of hopes for finding a second Earth. If the gas giant is real, those hopes are probably dashed. The habitable zone is occupied by a world that is fundamentally hostile to Earth-like conditions, and any Earth-like worlds that may have once existed there were probably destroyed by the gas giant's gravitational influence long ago. But I do not want you to walk away from this video feeling disappointed. Because the discovery of a gas giant in the habitable zone, while it may foreclose the possibility of an Earth-like planet, opens up entirely new possibilities that are, in their own way, just as exciting. Moons, as we discussed, could be habitable. And the mere existence of a planet in this system, regardless of its type, tells us something extraordinary about the ubiquity of planets in the universe. Furthermore, the destruction of Earth-like planets by a migrating gas giant is not unique to Alpha Centauri. It is thought to have happened in many planetary systems. In fact, some astronomers believe that our own solar system narrowly avoided a similar fate. There is evidence that Jupiter may have migrated inward early in the solar system's history, potentially as far as about 1.5 astronomical units from the Sun, destroying a generation of inner planets before Saturn's gravitational influence pulled it back outward. This hypothesis, called the Grand Tack model, suggests that the rocky planets we see today, including Earth, are a second generation, formed from the debris left behind after Jupiter's rampage. If this is true, then Earth's existence may be a fortunate accident, a consequence of Jupiter happening to be pulled back by Saturn before it could complete its destruction of the inner solar system. Alpha Centauri A, if it exists, may represent a system where no such rescue occurred, where the gas giant migrated inward and stayed, clearing the habitable zone of rocky planets and establishing itself as the dominant world. It is a cautionary tale from the cosmos, a reminder that the delicate, orderly arrangement of our solar system is not the norm, but the exception. And this too is valuable knowledge. Understanding why some systems produce habitable planets and others do not is one of the central goals of exoplanet science. Every system we study, whether it looks like ours or radically different, adds to our understanding of the factors that determine whether a planetary system can harbour life. Alpha Centauri, with its complex triple-star dynamics, its diverse collection of known and candidate planets, and its proximity to Earth, is a natural laboratory for studying these factors. And the JWST detection of S1 has turned the volume up to 11 on that laboratory. Let me also address something that might be nagging at some of you. The question of why this detection is being called strong evidence rather than a confirmed discovery. In science, there is a spectrum of certainty, and the language we use matters. A candidate is a possible detection that has not been confirmed by independent observations. Strong evidence means that multiple lines of evidence point in the same direction, that extensive analysis has failed to find an alternative explanation, but that the gold standard of confirmation, repeated independent detection, has not yet been achieved. A confirmed planet is one that has been independently verified by multiple observations and/or methods, leaving no reasonable doubt about its existence. Alpha Centauri A is currently at the strong evidence stage. The August 2024 detection, the consistency with the 2019 Velt observation, the inability to explain S1 as an artifact, and the orbital modelling that accounts for the 2025 non-detections all point toward a real planet. But the fact remains that S1 has only been clearly seen once, in a single observation from a single telescope. Until it is seen again, preferably at a position consistent with the predicted orbit, the scientific community will correctly withhold the label of confirmed. This caution is not weakness, it is strength. It is the immune system of science, protecting the body of knowledge from premature or incorrect additions. The history of exoplanet science is full of examples where caution was warranted. The retracted planet around Alpha Centauri B in 2012 is one. the long and tortuous saga of Fomalhaut B, initially heralded as the first directly imaged exoplanet and later reclassified as a dissipating dust cloud, is another. Science makes progress not by jumping to conclusions, but by carefully, methodically, painstakingly building a case that can withstand scrutiny. And that is exactly what the team behind this discovery is doing. They are building the case. Brick by brick, observation by observation, simulation by simulation. And the next brick will be laid in August 2026. Now I want to spend some time discussing the broader landscape of exoplanet science and where this discovery fits within it, because context is essential for appreciating the significance of any individual finding. As of today, we have confirmed the existence of nearly 6,000 exoplanets. They range in size from smaller than Earth to larger than Jupiter. They orbit every type of star, from tiny red dwarfs to massive blue giants. They have been found in every conceivable configuration: tight, circular orbits, wide, eccentric orbits, retrograde orbits that go backward compared to their star's rotation, orbits that carry them over the poles of their star rather than around its equator. Some orbit pairs of stars, circling both stars like a planet from Star Wars. Some orbit in systems of many planets packed close together, like TRAPPIST-1 with its 7 Earth-sized worlds. Some orbit in vast, lonely systems where they are the only known planet, wandering in the darkness of interstellar space. This diversity has demolished every preconception we had about what planetary systems should look like. Before the exoplanet era, most astronomers assumed that other planetary systems would look more or less like ours. Small rocky planets close in, gas giants farther out, everything on nice circular orbits. The reality turned out to be wildly different. Hot Jupiters, super Earths, mini Neptunes, eccentric giants, resonant chains, planets on polar orbits, all of these were surprises. The universe's imagination for planetary configurations turned out to be far more creative than our own. And within this diversity, a pattern has emerged that is particularly relevant to our story. We now know that planets are common in the habitable zones of Sun-like stars. The Kepler mission estimated that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. Given that there are hundreds of billions of Sun-like stars in the Milky Way alone, this implies that there are billions of potentially habitable worlds in our galaxy. Billions. But the vast majority of these are too far away to study in detail. We can detect them, measure their size and orbital period, and in some cases infer some properties of their atmospheres. But we cannot resolve them. We cannot take their pictures. We cannot study them individually with the kind of depth that would tell us whether they actually have oceans, continents, weather, or life. That is why Alpha Centauri is so special. At 4.37 light-years, it is the only system where we have a realistic chance of studying individual worlds in enough detail to answer these questions, at least with technology that is foreseeable in the coming decades. Every other habitable zone planet around a Sun-like star is too far away for the next generation of telescopes to resolve. Alpha Centauri stands alone as the one place where the dream of characterizing an alien world might actually come true. And now, with the JWST detection of a candidate gas giant in the habitable zone of Alpha Centauri A, that dream has taken on a new urgency and a new dimension. Because if the planet is confirmed, it will not just be a statistic, not just a data point in a catalogue. It will be a real individual world with its own history, its own dynamics, its own potential moons, its own mysteries to be unravelled. It will be a place we can point a telescope at and study for years, decades, even centuries, learning more and more with each passing year as our instruments improve. It will become a landmark in the human exploration of the cosmos, as significant in its way as the discovery of the New World was in the age of terrestrial exploration. Charles Beichman captured this beautifully when he said, "This would become a touchstone object for exoplanet science, with multiple opportunities for detailed characterization by Webb and other observatories." A touchstone. A reference point the planet that all other exoplanet observations are measured against, because it is close enough to study in depth and in detail. And Aniket Sanghi added, if confirmed, the potential planet seen in the Webb image of Alpha Centauri A would mark a new milestone for exoplanet imaging efforts. Of all the directly imaged planets, this would be the closest to its star seen so far. It's also the most similar in temperature and age to the giant planets in our solar system, and nearest to our home, Earth the closest. The most similar. The nearest. These superlatives are not hype. They are factual descriptions of a detection that, if confirmed, stands alone in the history of exoplanet science. I want to dwell for a moment on the human element of this story, because science is not done by telescopes and computers alone. It is done by people. People with ambitions, doubts, hopes and fears. People who spend years working on problems that might not pan out. People who have to convince skeptical colleagues, fight for telescope time, process mountains of data, and maintain their determination in the face of frustrating non-detections and ambiguous results. Charles Beichman spent nearly a decade championing this observation. From his 2017 email that essentially said, "I know this sounds crazy, but hear me out," to the August 2024 detection and the dramatic non-detections of 2025, he has been the driving force behind the project. Think about what that means. Spending years of your career on an observation that might not work, that might produce nothing but noise, that might be dismissed by the community as a fool's errand. That takes courage. That takes conviction. That takes the kind of stubborn, unreasonable optimism that has driven every great scientific advance in history. Aniket Sanghi, as a PhD student, took on one of the most challenging projects available. He could have chosen something safer, something more likely to produce a clean, publishable result. Instead, he chose the hardest target, the most demanding observations, the most complex data analysis. And it paid off, or at least it appears to have paid off, with a result that, if confirmed, will make his name in the field. The operations team at the Space Telescope Science Institute, who had to develop custom observing sequences for a target that Webb was never designed to observe, deserve recognition as well. They are the unsung heroes of this story, the people who made the impossible observation technically feasible. And the broader community of scientists who developed MIRI, who designed its coronagraphic masks, who built the cryocooler that keeps it at 7 Kelvin, who calibrated its detectors and wrote its data processing software, all played a role. Science is a collaborative enterprise, built on the accumulated work of thousands of people over decades, and this discovery is a product of that collaboration. Let me now turn to a question that I know is on many of your minds. What would interstellar travel actually look like in practice? And how might the discovery around Alpha Centauri influence the timeline and priorities of such a journey? If Breakthrough Starshot succeeds in developing its laser-driven light sail technology, the first interstellar mission would likely involve launching not one but hundreds or even thousands of tiny starships, accepting that many would be lost to equipment failures, dust impacts, and other hazards en route. The surviving craft would fly through the Alpha Centauri system at about 20% of the speed of light, taking images and measurements during a flyby lasting only a few hours. The data would be transmitted back to Earth using tiny onboard lasers, and we would receive the first close-up images of another star system about 24 years after launch. What would those images show? If Alpha Centauri A is real, the starships would fly past it at close range, capturing images of a gas giant world orbiting in the habitable zone of a sun-like star. They would be able to determine the planet's size, its cloud structure, possibly its ring system if it has one, and critically, they might be able to image its moons. Those moons, if they exist, could be resolved well enough to determine their size, surface reflectivity, and perhaps even signs of an atmosphere. Imagine the image, a Saturn-like gas giant banded with clouds of gold and brown, hanging in the glow of a star almost identical to our sun, with one or more moons visible as tiny dots of light nearby. And beyond, in the background, The other members of the Alpha Centauri system, the binary companion Alpha Centauri B, a warm orange light, and in the far distance, the faint red speck of Proxima Centauri. That image would be the most profound photograph ever taken. More profound than the Apollo 8 Earthrise, more profound than Hubble's deep field. It would be a window into another world, another system, another possibility for existence. And if those moons showed signs of an atmosphere, signs of water, signs of anything that hinted at habitability, the impact on human civilization would be incalculable. It would transform our priorities as a species. It would galvanize investment in space exploration. It would inspire a generation of scientists, engineers, and dreamers. And it would pose a question that we would be unable to ignore should we go there. Not with a 1-gram chip on a light sail, but with people? With human beings? Can we build a ship that could carry a crew across 4.37 light years of void and deliver them to a world that might be waiting for them? That is a question for future generations. But the seeds of it are being planted now. With every observation Webb makes, with every simulation Sanghi runs, with every laser test that Breakthrough Starshot conducts, with every paper that is published, and every telescope that is built. The future of interstellar exploration is being constructed, one piece at a time, and the discovery of a planet around Alpha Centauri A is one of the most important pieces. Let me also address one more scientific angle that deserves attention. The question of what the Alpha Centauri system can teach us about the formation and evolution of triple star systems in general. Triple star systems are not uncommon in the galaxy. Surveys suggest that a significant fraction of stars, perhaps as many as 10 to 20%, exist in triple or higher order multiple systems. These systems are dynamically complex, with gravitational interactions between the three bodies producing orbital configurations that can be stable, chaotic, or anything in between. The long-term stability of a triple system depends critically on its hierarchical structure. If two of the stars form a close binary and the third orbits at a much greater distance, the system can be stable for billions of years. This is exactly the configuration of Alpha Centauri, with A and B forming a relatively close binary and Proxima orbiting at an enormous distance. Studying planets in such systems tells us about the conditions under which worlds can form and survive in multi-star environments. Since a significant fraction of stars in the galaxy are in multiple systems, understanding planet formation in these environments is not an academic exercise, but a practical necessity for estimating the total number of habitable worlds in the Milky Way. If planets can form and survive in binary and triple systems, then the number of potential homes for life increases dramatically. If they cannot, then we must restrict our estimates to single-star systems. The Alpha Centauri system, being the closest and most well-studied triple system, serves as the testbed for these questions. The existence of planets around Proxima Centauri has already shown that planet formation can occur in the outer reaches of a triple system, around a star that is gravitationally bound to a binary pair but orbiting at a great distance. The potential existence of a planet around Alpha Centauri A would extend this to the inner binary itself, showing that planets can form and survive even in the gravitationally disruptive environment of two closely orbiting Sun-like stars. This has profound implications for the galaxy-wide census of habitable worlds. If planet formation is robust enough to produce gas giants in the habitable zone of a binary star, then smaller, rocky planets might be able to survive in such systems as well, at least in some configurations. The universe might be much more hospitable than we feared. Now, I've been talking for a long time, and I want to make sure that the full picture is crystal clear in your mind before we begin to wrap up. So let me walk through the entire timeline of events one more time, from beginning to end, laying out every key moment in this extraordinary saga. The story begins billions of years ago, when a cloud of gas and dust in the southern part of the Milky Way began to collapse under its own gravity. Out of this cloud, 3 stars were born: Alpha Centauri A, a G2V star nearly identical to our Sun; Alpha Centauri B, a slightly smaller and cooler K1V star, and Proxima Centauri, a tiny red dwarf. The three stars settled into a stable hierarchical configuration, with A and B orbiting each other every 80 years, and Proxima orbiting the pair at a vast distance, taking over 500,000 years to complete a single orbit. Around at least one of these stars, and probably more, planets formed from the leftover material of the stellar birth process. Around Proxima Centauri, at least 2 planets were confirmed: Proxima B, an Earth-sized world in the habitable zone discovered in 2016, and Proxima D, a tiny sub-Earth discovered in 2022. A third, Proxima C, remains disputed. Around Alpha Centauri A and B, no planets were confirmed despite decades of searching. In 2012, a claim of an Earth-mass planet around Alpha Centauri B was retracted. The binary stars seemed stubbornly planet-free. In 2017, Charles Beichman proposed using the yet-to-be-launched James Webb Space Telescope to search for planets around Alpha Centauri A using direct imaging with the MIRI coronagraph. The idea was considered audacious, perhaps reckless, given the extreme challenges involved. On December 25, 2021, JWST was launched into space. Over the next 2 years, it was deployed, commissioned, and began its scientific observations, quickly producing stunning results on distant galaxies, exoplanet atmospheres, star-forming regions, and solar system objects. In 2019, separately, the NEAR experiment on the Very Large Telescope in Chile detected a faint thermal signal near Alpha Centauri A that was consistent with a planet but remained inconclusive. This result was published in Nature Communications in 2021. In August 2024, Beichman, Sanghi, and their team finally got their chance. JWST turned its MIRI coronagraph toward Alpha Centauri A, using a custom observing sequence developed by the Space Telescope Science Institute and an innovative reference star subtraction technique. The team detected a faint source, S1, at approximately 2 astronomical units from the star, over 10,000 times fainter than Alpha Centauri A. The signal was consistent with a Saturn-mass gas giant in the habitable zone. In February 2025, using director's discretionary time, JWST observed Alpha Centauri A again. S1 was not detected. In April 2025, JWST observed again. S1 was still not detected. The team ran computer simulations of millions of possible orbits, incorporating the 2019 fault hint, the 2024 detection, the 2025 non-detections, and the constraint of orbital stability in the binary system. They found that approximately half of all plausible orbits would place the planet too close to the star to be detected in February and April 2025, explaining the non-detections without disproving the planet. On August 7, 2025, the results were announced in 2 papers accepted by the Astrophysical Journal letters. The candidate was presented as strong evidence for a gas giant in the habitable zone of Alpha Centauri A, the closest such candidate ever found. The astronomical community responded with cautious excitement. Experts praised the ambition and rigor of the work while noting the need for confirmation. And now, in 2026, we wait. August 2026 is the next observation window, the moment when Webb might see S1 again and either confirm the planet or deepen the mystery. That is the story. Complete, detailed, every twist, every turn, every piece of evidence laid out for you to examine. But before I close, I want to leave you with a few thoughts that go beyond the science. We are living in an extraordinary moment in the history of our species. For the first time, we have the tools to find other worlds, to study them in detail, and to ask whether they harbour life. For the first time, we have serious, funded, peer-reviewed research programs aimed at sending spacecraft to other stars. For the first time, we have a candidate planet in the habitable zone of the nearest Sun-like star, a world that might have moons, that might have water, that might have conditions suitable for biology. These are not science fiction fantasies. These are realities of the early 21st century. And I want you to appreciate how remarkable this is. For most of human history, the stars were unreachable and unknowable. They were gods, or jewels, or pinholes in the vault of heaven. They were everything our ancestors could not understand. And now, in the span of a few decades, we have gone from not knowing whether any other star had planets to finding nearly 6,000 of them. We have gone from wondering what the stars were made of to having detailed spectroscopic models of their composition. We have gone from dreaming of visiting other worlds to designing actual spacecraft that could make the journey. This acceleration of discovery and capability is not going to slow down. The next decade will bring Roman, the ELTs, new space missions, new instruments, new techniques, and new surprises. 20 years from now, the current state of our knowledge about the Alpha Centauri system will seem as quaint and incomplete as what we knew 20 years ago seems to us now. The pace of progress is breathtaking, and we are lucky, profoundly lucky, to be alive at this particular moment in the story.